Good morning, learners and viewers. Welcome to the session for quantitative analysis for managerial application MMPC005. Today we will be discussing about Unit 10, that is sampling distribution. First of all, the thing is that what is actually meant by sampling distribution? Sampling distribution of a given statistic is the distribution of the values taken by the statistic in all possible samples of the same size from the same population. Or in other words, we can say that if we repeatedly collect samples of the same sample size from the population, compute the statistics, that is mean, standard deviation, proportions, and then we draw a histogram of those statistics, the distribution of that histogram tends to have is basically called the sample distribution of that statistics. Sampling distribution of means and the central limit theorem. Sampling distribution of sample means form. Basically, it is taken from normal population. Now the theorem states that if X be the sample mean of a random sample size small n drawn from a population having a mean m and standard deviation s, then the mean of x bar is mu x bar equal to m, and the standard deviation is sigma x bar is equal to sigma divided by under root n. After selecting a sample, one would like to go for estimating the value of a population parameter, testing a statistical hypothesis about the population, comparing two or more populations, and performing correlation and regression analysis. This is normally what we do. Sampling, we start with sample distribution. Sample statistics is a function of n samples. Values are from x1, x2 till xn. And sample statistic is a random variable and therefore has a probability distribution or a probability density function. What in short we call it as P. It is also known as the sampling distribution of the statistic. Sample statistics form the basis of all inferences drawn about the populations. Probability distribution of the sample statistic allows us to calculate the probability that the sample statistic assumes a particular value. This ability to calculate the probability that the sample statistics lie in a particular interval is the most important factor in all the statistical inferences. Mathematically, we will see as per their notations. Sample is x1, x2 till xn. Sample mean, normally, it is summation of all the observations divided by number of observations. Here, the sample mean will be x bar equal to x1 plus x2 plus xn till xn divided by n. For another sample of size n from the same population, we might get a totally different set of sample values, and so a different sample mean will be there. There are many, perhaps infinite possible values of a sample mean. Sampling from infinite population. When population is infinitely large, population mean is mu, and population variance is sigma square, and we are doing sampling without replacement. Here, the standard deviation of sample mean is also called the standard error of the mean. The standard error of mean indicates the extent to which the observed value of the sample mean can be away from the true value due to sampling errors. Mathematically, how to denote all these terms? E x bar is equal to mu. If we talk about the variance x bar is equal to sigma square upon under. As we have already discussed about the standard error, the standard error of the mean is sigma x bar equal to sigma upon under root. If now the condition is different, here random variables do not remain independent. You see, there is a change now. That is, E x bar is equal to mu, that is the same, but variance has changed. That is, V x bar equal to sigma square upon n into n minus n divided by n minus 1. Now, these all values have the same meaning. Standard area of the mean here will be sigma x bar equal to sigma upon under root n into under root n minus n upon n minus 1. This factor, under root n minus n upon n minus 1, is called finite population multiplier. Now, sampling from normal population. If x is equal to, if x tends to n mu sigma square, that means these are the conditions, then we follow that. X bar tends to n mu sigma square. This distribution is a continuous distribution, and so the population cannot be small and finite if it is distributed normally. Now we will see a problem. What we discuss how this is basically applied in a practical problem. Suppose the diameter of a component produced on a semi-automatic machine is known to be distributed normally with a mean of 10 mm and a standard deviation of 0.1 mm. If we pick up a random sample of size 5, what is the probability that the sample mean will be between 9.95 mm and 10.05 mm? We have to find the probability of diameter of a component between 9.95 mm and 10.05 mm. When we are going to convert this into a mathematical application, we can see that probability 9.95 is less than equal to x bar less than equal to 10.05. We are aware of it is normally distributed as it is already stated in the numerical problem. We will see, we will apply 9.95 minus 10 upon 0.1 divided by under root 5 less than equal to x bar minus mu upon sigma divided by under root n, which will be less than equal to the second value, that is 10.05 minus 10 upon 0.1 divided by under root 5. All these values are given to us in that problem. After solving it, we will get minus 1.12 should be less than equal to z, should be less than equal to 1.1. That means it has to be in between minus 1.12 and plus 1.1. Since the values are same, so we will be taking the positive side and we will be multiplying the probability by 2. Now, referring to normal distribution table, for z equal to 1.12, we will get the value as 0.3686. We will be multiplying this value by 2 and we will get 0.7372. That means the probability that the sample mean will be between 9.95 and 10.05 is 0.737. That means almost 73% or 74%. This is how it is drawn in respect of normal distribution. You have to calculate the area between the shaded region. Now, we move on to next part, that is central limit theorem. If x1, x2 till xn are n random variables which are independent and having the same distribution with mean mu, and standard deviation sigma. We are aware of that n tends to infinity, that is n is too large. The limiting distribution of the standardized mean will be z equal to x bar minus mu divided by sigma upon under root n, which is a standard normal variant. A sample size larger than 30 is generally considered to be large. Now, students t distribution. In actual practice, the value of population standard deviation sigma is often unknown, which makes it necessary to replace this with an estimate. Usually by S, the sample standard deviation. In place of sigma, we are going to use S. Formula will remain the same. X bar minus mu upon sigma divided by under root n will be changed by x bar minus mu upon S divided by under root n. Exact sampling distribution is also used for t distribution. Now here in t distribution, if x is a random variable having the standard normal distribution and y is a random variable having a chi-square distribution with v degrees of freedom, and if x and y are independent, then the random variable is given by t equal to x upon under root y upon v, which has a distribution called as t distribution or the student's t distribution with v degree of freedoms. There are many t distributions, each with its degree of freedom, which is the only parameter of this distribution. A t distribution is similar to standard normal distribution. You can see in the figure. By increasing the degree of freedom, you can see that its position is widening out. At the top, standard normal distribution or t distribution with infinity degree of freedom, similar to normal distribution. T distribution with degree of freedom, and the dotted line is t distribution with distribution, the degree of freedom between infinity and t distribution. As the degree of freedom increases, the t distribution comes closer to the standard normal variant, and when the degree of freedom becomes infinitely large, the t distribution and the z distribution becomes indistinguishable. That means it is converted into normal variant. T distribution in practice, we conclude that x bar minus mu upon s upon we are aware of it. That is applicable when t distribution with n minus 1 degree of freedom. It is therefore possible to know the sampling distribution of x even when sigma is not. This result is usually useful when the sample size is not very large. As we have seen earlier, if the sample size is large, the t distributions with large degree of freedom can be approximated as z distribution. Now, t distribution is used when the degree of freedom are not larger than 30. If the degree of freedom are larger than 30, the t distribution is approximated by the standard normal or the z distribution. If n is sufficiently large, that means what we are going to convert, we have to find out the probability, and it will be a function of b, b into 1 minus b. That is, in other terms, we can say that is q, pq upon n. This approximation works quite well if n is sufficiently large so that both nb and n into 1 minus p, that is nq, are at least as large as 5. Now, interval estimation. Suppose we want to estimate the mean income of population of households residing in a part of a city. How we will do? what are the possible outcomes we will think of? We might proceed by picking up a random sample of 100 households from the population and calculate the sample mean, that is, the mean income of 100 sample households. And in the absence of any other information, the sample mean can be used as a point estimate of the population mean. The lower the standard error of the mean, the greater is the confidence on the correctness of our estimation. This process is further refined in interval estimation, wherein we present our estimate as an interval and quantify our confidence so that the true population parameter is contained by the estimated interval. Now, what is basically meant by confidence interval? The probability that the interval estimate will contain the true value of the population parameter that is being estimated. If we say that 95% confidence interval for the population, which means it is obtained by spanning 1.96 times the standard error of the mean on either side of the sample mean. We mean that if we take a large number of samples of size n, say 1000, and obtain the interval estimate from each of these 1000 samples, then 95% of these intervals estimate would contain the true population. Suppose it is known that the weight of cement packed in bags is distributed normally with a standard deviation of 0.2 kg. A sample of 25 bags is picked up at random, and the mean weight of the cement in these 25 bags is 49.7 kg. We want to find a 90% confidence interval of the mean weight of the cement in filled bags. Now, what information is given to us? It is a problem which is distributed normally. That means we can say that X is normally distributed within standard deviation of 0.2 kg. Now, what is the standard error of the mean? We have the formula of sigma x bar is equal to sigma upon under root n. We are having the value of standard deviation, that is 0.2. We have the value of n, that is under root n is 25. When we are going to divide it, it comes out to be 0.04 kg. Now, since n is less than 30, we will use t-distribution. For that, we will be using the formula t is equal to x bar minus mu upon sigma divided by under. We have the value 1.64 equal to 49.7, the mean, minus mu upon your standard deviation is 0.2 divided by under 25. When we are going to evaluate it, we are going to get the value as mu equal to 49.7 plus minus 1.645 into 0.04. Two individual values will be there. The first one will be 49.63 and the second one will be 49.76. That means mu will lie between 49.63 and 49.76 with 90% of confidence. Now, how to calculate the sample size? As a matter of practice, statisticians usually consider samples of size 30 or more to be large. In the popular large sample case, a 95% confidence interval estimate for the population, the mean is given by x bar equal to 1.96 sigma upon n. Now, sample size for estimating population mean. We assume that population distribution is normal and the population standard deviation is normal. In such a case, the sample size required for a given confidence level and a required accuracy can be easily determined. We will go back to the same problem. Suppose we know that the weight of the cement in filled bags is distributed normally with a standard deviation of 0.2 kg. We want to know how large a sample should be taken so that the mean weight of the cement in a filled bag can be estimated within plus or minus 0.05 kg of the true value with a confidence level of 90%. Here, we have to calculate the interval. So we know the standard result for 90% of confidence level, that is x bar plus minus 1.645 into sigma 100, which contains the true value of the population mean 90% of the time. We also want that the interval x minus 0.05 to x plus 0.05 should be given as a 90% confidence level. We have to calculate the value of n. You know that 1.645 sigma per 100 root n is equal to 0.05. On calculating the value of n, we get as 43.3. The numbers backs will be a number only. It won't be in decimal, so that we will be converting it into 44. So the sample size of at least 44, so that the mean weight of the cement in a filled bag can be estimated within plus or minus 0.05 kg of the true value with a 90% confidence level. Now, we move on to unit 11, that is testing of hypothesis. First of all, we will try to understand what is actually meant by hypothesis. When we study a class of problems where the decision made by a decision maker depends primarily on the strength of the evidence thrown up by a random sample drawn from a population. To test a hypothesis, a statistical procedure is followed. This procedure is known as testing of hypothesis. Hypothesis, or more specifically, a statistical hypothesis, is some statement about a population parameter or about a population distribution. If the population is large, the hypothesis is tested on the basis of the outcome of a random sample. A hypothesis is a statement about a population parameter or about a population distribution. In any testing of hypothesis problem, we are faced with a pair of hypotheses such that one and only one of them is always true. One of this pair is called the null hypothesis, and the alternate one, and the other one is alternate hypothesis. The null hypothesis is represented by H0, and the alternative hypothesis is represented by H1. Now, what is actually meant by null hypothesis? Null hypothesis is called by its name because in many situations, acceptance of this hypothesis would lead to null action. Rejecting the null hypothesis leads to a change in status quo. If the population mean is represented by, we can set up our hypothesis as H0. This is the standard how H0 and H1 are denoted. H0 is to mean is equal to 20, and the other one, alternate one, H1 is to mean should be greater than 20. What we have represented symbolically above can be interpreted to mean that the null hypothesis is that the population mean is not greater than 20, whereas the alternate hypothesis is that the population mean is greater by 20. It is clear that both H0 and H1 cannot be true, and also that one of them will always be true. At the end of our testing procedure, If we come to the conclusion that H0 should be rejected, then this also amounts to saying that H1 should be accepted and vice versa. Now, while doing this interpretation, we may draw wrong conclusions. This arises due to the types of error. There are two types of error, type 1 and type 2. If we wrongly reject H0, when in reality H0 is true, the error is called type 1 error. Similarly, if we wrongly accept H0, when H0 is false, the error is called type 2. Now, you can see if H0 is true, we have to accept H0. If we reject H0, then it is a type 1 error. If H0 is false and we reject H0, then it becomes a type 2 error. We see how all these are calculated. We take up a situation where a patient suffering from high fever reaches to a doctor. And suppose the doctor formulates the null and alternate hypothesis as H0. The patient is a malaria patient. H1, that means the alternate. The patient is not a malaria patient. Now, what are the different cases? There will be 4 cases. We will see how these 4 cases will be used in our hypothesis terms. Suppose that hypothesis H0 is really true. That is, the patient actually a malaria patient, and after observation, pathological and clinical examination, the doctor rejects H0. That is, he or she declares him or her a non-malaria patient. It is not a correct decision, and he or she commits an error in decision, which is known as type 1 error. Now, in case 2, suppose the hypothesis H0 is actually false. That is, patient actually a non-malaria patient, and after observation, the doctor rejects H0. That is, he or she declares him or her a non-malaria patient. It is a correct decision over here. Case 3 becomes, suppose that the hypothesis H0 is really true. That is, patient actually a malaria patient, and after observation, the doctor does not reject H0. That is, he or she declares him or her a malaria patient. It is a correct decision. But in case 4, suppose the hypothesis H0 is actually false. That is, patient actually a non-malaria patient, and after observation, the doctor does not reject H0. That is, he or she declares him or her a malaria patient. It is not a correct decision, and he or she may commit an error of decision making, that is known as type 2 error. Both these errors are bad and should be reduced to the minimum. For a given sample size, these 2 errors neutralize each other. If the testing procedure is designed as to reduce the probability of occurrence of type 1 error, simultaneously the probability of type 2 error would go up and vice versa. What can at best be achieved in a reasonable balance between these 2 errors? Type 1 error is much more severe than type 2 error, and so needs to be controlled. Type 1 error generally results in a financial loss to the company, and type 2 generally results to an opportunity loss for the company. Now we will talk in terms of significance level. Probability of type 1 error needs to be controlled. This is done through specifying a significance level at which a test is conducted. The significance level, therefore, sets the limit to the probability. of type 1 error, and test procedures are designed so that to get the lowest probability of type 2 error subject to the significance level. The probability of type 1 error is usually represented by the symbol alpha, and the probability of type 2 error is represented by beta. Testing of hypothesis suffers from the limitation that the financial or the economic cost of consequences are not considered explicitly. In practice, the significance level is supposed to be arrived at after considering the cost of consequences. It is very difficult to specify the ideal value of alpha. Probability of type 1 error should be lower, that is, the value of alpha should be lower, and in practice most tests are conducted at alpha equal to 0.01, alpha equal to 0.05, or alpha equal to 0.1 by the convention as well as by the convenience. Now mathematically, graphically we can see how this type 1 error and alpha are related. The level of significance is 0.01, which is type 1 error. We can see that often we accept null hypothesis and rarely rejects a null hypothesis even if it is false. Here, the acceptance region is big. When the significance level is equal to 0.5, that is again a probability of type 1 error. Here we can see that the area has reduced. Rarely accepts a null hypothesis, often rejects a null hypothesis when it is true. Now we will see some examples where these types of errors are committed. In testing of a chemical, if wrong inferences, whole group of users will be well. So we prefer high significance level, high probability of type 1 error, and we reject X naught when it is true. Second part, reassembling a big machine. If wrong inferences, some parts may be repaired or replaced. We prefer low significance level because there is a high probability of type 2 error. That means part has to be replaced, but due to some or the other reason, we avoid it and we don't do it. And we have to later pay the price of the decision what we have not actually taken. Now, effectiveness of a drug. If H0 had no effect and H1 it had effect. So what we are going to do? We are finding out a 5% level of significance, and we accept means at 5% of significance, data does not allow us to reject a null hypothesis. You can see that mean will be between mean minus 1.96 of SD, and on the right side it will be mean plus 1.96 of the SD. The significance region of the no significant difference is in between. Now, power curve for test. Calculate the probability of rejecting H0 for different values of mean, and we plot these on a graph. Such a graph is known as power curve of a test. Here, H0 is at the value of mu is less than equal to 20, and the alternate will be mu is greater than 20. When we are going to plot it on a graph, we will see there are two graphs when the graph with the bold line and the graph with the dotted line. If we reject H0, if X bar is greater than or equal to 20, it will be a bold line graph. And if we reject H0 at X bar equal to or greater than 20.6, we are going to get a dotted line. But the actual part is from where this graph starts. We have to see a value nearer to 20. It will start from here. But as you are aware of, This again graph is not going to touch your axis line. P-value of a test. The significance level is arbitrarily fixed. A better way of expressing the conclusion of a test is a state that the p-value of or the probability value of the test. If p-value of test expresses the probability of observing a sample statistic as extreme as one can observe if the null hypothesis is true. Now, what is the procedure of testing the hypothesis? There are two phases. Basically, there are two phases in testing of the hypothesis. In the first phase, we design the test and set up the conditions under which we shall reject the null hypothesis. The second phase is we use the test based on the sample evidence and draw our conclusion as to whether the null hypothesis can be rejected, or else we use what is the p-value of the test. Now I will tell you what are the actual procedures, what we are doing. When a problem is given to us, to how that is going to step. Step one is state the null and alternate hypothesis as in H0 and H1. We choose the test statistics, that is, the sample statistic that will define the critical value. Third one, specify the level of significance, that is the value of alpha. Fourth one, we define the critical region in terms of the test statistic. Fifth one is we compare the observed value of the test statistics with the cutoff value or the critical value and decide to accept or reject the null hypothesis. These are the basically 5 steps which are normally followed. Now the question is, what is needed? Inspections sometimes do not allow us to get inferences. For example, a manager comments that average work efficiency is 90%. Then, to suppose our calculation gives result as 95%, we accept, 40% we reject, and 89% we have to apply something. Now, institutions does not work, so one has to decide on the basis of sample information. Testing of population mean. Under different conditions, the test procedures have to be developed differently, depending upon the problem. There are many cases like when the population variance is known or unknown, when the distribution of samples mean Z can be approximated by a normal distribution, when test is two-tailed test or one-tailed test. Now, we'll see how we take a call what to do. That is, what type of distribution we have to use. If we talk in terms of the normal distribution or t-distribution, these are two conditions. When the sample size is larger than 30 and the population standard deviation is known, we use that test. But sample size is larger than 30 and you are not aware of the standard deviation of the population, then we use that test. But if the sample size is larger than 30 and population standard deviation is known, we can use that test. But when standard deviation is not known, we apply t-test. So this is how the inferences are drawn initially. Now, we'll see how these factors come into. Normally, how they are applied in problems. Suppose we talk about a bulb manufacturer. Reject if life is short, that is, it is of bad quality. And reject if life is very high. That means that will be a case of large production cost. Mathematically, when we convert it into this, in terms of hypothesis, this is what we draw. H naught is to mu is equal to mu H naught. And H naught mu is not equal to mu H naught. Graph. Your graph will be of this type. But if we talk about the niche quality of the bulb in terms of bulb holes, we reject if life is shorter. That means different quality. And we accept otherwise. Who is bothered about the cost? Wholesaler is never worried about the cost. His part is to sell off. And if the quality is not good, he is going to say, no, I'm not going to purchase the material. So see the difference of the two different conditions in terms of a bulb manufacturer and a bulb wholesaler. How they are doing, both of them are doing business, but their priorities are different. Here in this case, H naught is mu is equal to mu H naught, but here H naught is to mu should be greater than mu H naught. We will be talking about that side of the graph. So these are the two comparisons. Now, here we see that how this comes into in problem solving. Suppose we talk about our ring manufacture. If the conditions are it must withstand 80,000 kg per square inch the load, and your standard deviation is 4,000 kg per square inch, and your mean is 9,600 kg per square inch. Mathematically, we are going to convert it into mathematical terms. Mu n is equal to 100. H naught mu is equal to that. It must withstand 80,000. That means the null hypothesis will be H naught mu is equal to 80,000, and your alternate will be H1 mu is not equal to 80,000. We have normally we select alpha equal to 0.05. We have to calculate standard error of mean, that is sigma x bar is equal to sigma upon under root. You are aware of sigma, that is 4,000. You are aware of n, that is 100 under root of 100 is 10. This comes out to be 400. Now we have to calculate Z. Z calculated because we are calculating it as per the conditions given in the problem. That means x bar is equal to mu h naught upon sigma upon under root by placing up the values. Now, how to conclude? If Z calculated, what we are calculating for this problem, is less than Z tabulated, what will be the value from the table? We accept the null hypothesis. And if your Z calculated is greater than the tabular value, then you reject it. This is how the conclusions are drawn. The condition here is your SD is 0. Now, another case is test of proportions. Here, testing the probability of employees. Here, H naught is roughly 80% of our promoted. Committee finds that only 70% are promoted. Suppose your n is 150, H naught is equal to 0.8, because it is something related to in terms of probability. That means Q H naught will be 1 minus 0.8, that is 0.2. What the committee concludes, that is P is equal to 0.7, Q will be 0.3, 1 minus P, and your alpha will be 0.05. Here, we are going to use a standard error of formula, that is sigma P bar, which is equal to sigma PH naught, QH naught upon N. All the values are available to us. We get the value of 0.03. What we are going to calculate the value of Z, that is that calculated is equal to P bar minus PH naught sigma P. All the values are. After calculating, the conclusion has to be found. If Z calculated is less than Z tabular, we accept the hypothesis. And if Z calculated is greater than Z tabular, then we reject the hypothesis. Here we have to test the mean when standard deviation is not. That means the problem is related to testing of recruitment scores. H naught This it is going fine. The average score on the aptitude test will be around 90. So your H naught will be equal to 90 and mu H naught will be 90, n is equal to 20, x bar is equal to 84, s is equal to 11, and here alpha we are using 0.10. We are not aware of anything which is related to sigma. Sigma is unknown. So what we are going to do? We have the sample size, that is s is equal to 11. For our calculation purpose, we are going to replace sigma by again calculating. If the t calculated is less than t tabular, we are using t test. We accept it. If t calculated is greater than t tabulated, we reject it. Now, we move to unit 12, that is chi-square test. Chi-square test will be used with a term that is degree of freedom. We have already discussed it. This is something, a test which has a thing in common, that is the degree of freedom. It is required the equality of variances would be tested. We can also test if the population distribution is really normal. We can test whether the population distribution is Poisson, exponential, or any other known distribution. Or we can test if two samples are independent. These are the conditions where we apply chi-square test. Now, if 1 degree of freedom is there, you see a graph which is coming down. If the degree of freedoms are increased, you can see it is becoming a bell shape. And if degree of freedoms are too large, we can see that it is becoming symmetrical or equivalent to a Z graph, that means under normal condition. Now, what are the properties of chi-square? If x is a random variable having a standard normal distribution, then chi-square will have a chi-square distribution with 1 degree of freedom. If y1 and y2 are independent random variables having chi-square distribution of v1 and v2 respectively, then y1 plus y2 will have a chi-square distribution with v1 plus v2 degree of freedoms. If we have n minus 1 degree of freedom, so we can use this formula, n minus 1 s square upon sigma square. Now, how this is used? A TV channel program manager wants to know whether there are any significant difference among male and female viewers between the type of programs they watch. A survey was conducted for this purpose, and the following results were obtained. There are two types of TV programs, that is news and the serials, and the viewers' sex will be male or female. If we talk in terms of news, 30% of the male are there, and 40% of the females are there, 10% of the females. In total, that is 40. And in case of serials, 20% of the male members are there, and 40% of the female are there. That means when we conclude, it becomes 60. And we are totaling it becomes 100. And when we are totaling male and female, it is again coming out in terms of 100. We will calculate chi-square statistics and determine whether type of program is independent of viewer's sex. We take 0.10 significance level. Now, how to define? First step is how to define a hypothesis. H naught is a null hypothesis. The viewer's sex is independent of the type of the program. That means there is no association among the male and female viewers. H1 will be the viewer sex is not independent of the type of TV program. Here, we are having observed frequencies of the viewers. We have to calculate expected frequencies. It is basically calculated by a formula or a relation, row total into column total divided by total. Here we will see. The problem is given to us. When we are finding out the expected frequency, what we are doing, 40 into 50 divided by 100 comes out to be 20. And for female, 40 into 50 divided by 100, which comes out to be 20. And we are adding up, it becomes 40. Again, for serials, 60 into 50 divided by 100, which is 30. And for female, it is 60 into 50 divided by 100, that is 30. When we are going to add up, we are going to 60. Total should remain 100. We arrange the data of the observed and expected frequency and we calculate G-square. This following table is true. For row 1, row column 1. The observed frequency, that means we are converting this data into this form. Your observed frequencies were 30, 20, 10, and 40. The respective 4 Asia units. These 4 values are there. We have to calculate it. What we have calculated the expected frequency, that is EI. That is 20, 30, 20, 30. First of all, we will calculate the difference between the observed frequency and the expected frequency. This comes out to be 10 minus 10 minus 10 and 10. We square it. 100. And finally, we have to calculate OI minus EI whole square divided by EI. That means this comes out to be 5, 3.33, 5.0, and 3.33. When we are totaling up, we are totaling sigma G square, which comes out to be 6.66. We have a 2 by 2 contingency table. The degree of freedom is R minus 1 into column minus 1. We were having 2 units. 2 minus 1 is 1. And again for column we have 2 minus 1, that is 1. That means we have 1 degree of freedom, and at 0.10 significance level, the tabular value is 2.706. And our calculated value is 16.66. How this conclusion is drawn? Since the calculated value is 16.66, which is greater than the tabular value, 2.706, we reject the hypothesis and conclude that the type of TV program is dependent on viewers' sex. It should therefore be noted that the value of G square is greater than the tabular value of G square. The difference between the theory and observation is significant. Then comes your testing the goodness of fit. The Chi-square goodness of fit is a statistical hypothesis test which is used to determine whether a variable is likely to come from a specified distribution or not. It is often used to evaluate whether sample data is repetitive or not. The goodness of fit test is typically used to determine if data fits a particular distribution. The test of independence make use of a contingency table to determine the independence of the two factors. The two are sometimes confused but they are quite different. The Chi-square test for independence compares two sets of data to see if there is any relationship among them. The Chi-square goodness of fit is to fit one category variable to a distribution. Suppose if you want to test if a worker is equally prone to producing defective components throughout an 8-hour shift or not. We break the shift into 4 2-hour slots and count the number of defective components produced in each of these slots. At the end of 1 week, we find that the workers have produced 50 defective components in the following breakup. This is the breakup. This is the outer frequency what we have portrayed. We have divided the time into 4 slots, and the error what they were committing has been. That means by using the significance level of 0.05, is it reasonable to assume that the probability to produce a defective component is equal in each of the 4 slots? We have to calculate the expected frequency. Here, what is happening? H naught, yes, B1 equal to B2 equal to B3 equal to B4, which is 0.25. And your alternate hypothesis that H1 will be B1, B2, B3 are not equal. We are provided with time slots and observed frequency. We have to calculate the expected frequency. We have calculated expected frequency as 12.50, 12.50, 12.50, and 12.50. We have to calculate OE minus EI. Next step is to square it, and the last column states that OI minus EI whole square divided by EI. Now we see that if the observed frequencies are 50, expected frequency is 50, that means our calculation is correct. And your G square is 3.28. This is your calculated value. That's for K minus 1, there are 4 values. 3. Degree of freedom will be N minus 1, that is 3 minus 1. But 3 degree of freedom at 0.05 level, significance level, your expected value or the tabular value is 7.815. Your calculated value is 3.28. We can reject the null hypothesis only when the observed value of the chi-square statistics at least 7.8. As your observed value of chi-square statistics is only 3.28, we cannot reject the null hypothesis. This is how inferences are drawn. Testing of hypothesis for 2 population variants using F-test. Before applying test for difference of 2 population means, one of the requirements is to check the equality of variance of the 2 populations. This assumption can be checked with the help of F-test for 2 population variances. For example, an economist may want to test whether the variability in incomes differ in 2 populations. A quality controller may want to test whether the quality of the product is changing over time, etc. Now, what are the assumptions? What we normally do? Assumptions for F-test for testing the variance of 2 populations are: population from each which the samples are drawn must be normally distributed, and the sample must be independent of each other. With this, we will be concluding today's session, and in our next session, we will continue with block 4.